Okay, so we start with the new topic. Till now, we have been studying kinematics, both in analysis and synthesis. Now we start with dynamics. So, machine dynamics, in other words, the way the chapter in the book is named, dynamic force and motion. Now, as you see, there are two topics here. One is dynamic force analysis, the other is dynamic motion. So we are basically talking about two problems. So in problem 1, we know enough information about the position, velocity, and acceleration of all the links at every instant of interest. So typically, the exercise problem talks about one instant. But in the practical problem, you would be knowing the full trajectory. And you will be required to find the required forces or torques of actuation. That is, actuation forces or actuation torques required to drive it according to that planned motion. And the corresponding joint reactions also you may need to find. Now, the joint reactions are needed in order to design the joints for sufficient strength and stiffness, and the actuator forces, actuator torques are needed to control them. Okay? So this problem is, or this activity is called dynamic force analysis, or in some contexts it is also called inverse dynamics. Why inverse dynamics? Because here you know the motion and you want to determine the effort, actuation forces. You see that dynamics ensues when you put an effort, and as a result of it, to causality, the motion takes place. You really don't give any motion to it. Okay. So, for example, when I pick up this pen, I really don't give it motion. I give it forces. And as a result of the forces I give, through laws of nature, the motion takes place. So the forces are the causes and the motion is the result. So here the result is known, the causes are to be determined. And so it is an inverse. The resulting motion is known and the forces causing that motion have to be found. Incidentally, in this case, the inverse problem happens to be easier. The second problem is the other way. The actuation forces or actuation torques are known in advance, and for all time instants for which you are interested, and sufficient information about position and velocity at one time instant known as the initial condition, and you need to find out the result. Here the causes are given and the result, the motion, is 1. So that is why it is called forward. Causes are known, effects are given. Or it is also called dynamic motion. This happens to be more difficult problem. So let us see how the two problems work out for simple analysis. So to begin with, forward analysis. And even before that, to begin with, let us quickly review the fundamental principles that we will be using in that. The entire kinematics that we have studied earlier, based on geometry and so on, that is already in our head. More than that, what comes from dynamics? The dynamic equations for a rigid body. There are three possible kinds of formulations that are quite often used in this kind of mechanical systems. One is Newton's law, you know, the vector sum of forces on a rigid body is equal to mass into acceleration of the center of mass, acceleration of the C. So this is the Newton. Now this is Newton's, and the corresponding Euler's equation out of that will be the sum total of moments on a rigid body. Now this includes direct moments as well as moments of all the forces. About the point G, about the CG, is equal to moment of inertia of the rigid body about the same point in the alpha. And make note that we are talking about plane motion. That's why this becomes so simple. In the case of 3D motion, these are a little more complicated. And for plane motion, force, acceleration, these things you have to take as vectors. But moment, angular acceleration, these things you can take as scale. And therefore, moment of inertia also will look like a scalar. Though in actual fact, in 3D motion, the thing is actually a tensor. Anyway, so this is a nuclear formulation. An equivalent and obviously equivalent formulation is the real inverse formulation. And algebraically, it will look like really nothing big deal, no big deal. This m into ag is taken on the other side of the equality as minus m into ag, and this minus m into ag, the bracketed thing, is sometimes called the inertia force. You already know that, and that is equal to 0. Similarly, so this is the D'Alembert formulation, which is obviously equivalent to this. Now, something else which is also equivalent to this or this, but not so obviously, is the Lagrange formulation. It is a beautiful formulation for dynamics, and here you say that there is a quantity of the dimension of energy, which is the sum total of the kinetic energy of the entire mechanics group. Okay. Now this is not on a rigid body. These two were on individual rigid bodies. Now this is entire mechanics group, all the rigid bodies involved in that. The sum total of all the kinetic energy minus sum total of all the potential energy, and this difference is called the Lagrange. Now you say that the natural motion takes place along those trajectories along which the integral of this Lagrangian with respect to time, which is called action, that action happens to be zero. And when you impose this condition, the first order necessary conditions of this S, the action being minimum, then you get a complicated kind of equation. That is, this L is to be differentiated with respect to a velocity coordinate and then partially. And then that has to be differentiated with the time total. And from that, you have to subtract the partial derivative of the same Lagrangian with respect to the corresponding position coordinate, and that turns out to be equal to the generalized force corresponding to that particular generalized force. Now, generalized, it is say Because if this qi, the ith coordinate is a position coordinate in the dimension of length, then this will be force. If qi is in the dimension of an angle, then it will be moment. Right. So this also happens to be equivalent to this or this, and you can actually derive Newton's law from this information. But that is a matter of classical analysis. We don't go. This Lagrange formulation I just wanted to mention as information, right? So that you feel motivated towards studying the few other things, which are very interesting. Now, on this, there are 2 points which you can keep in mind. One is that sometimes, for the convenience of your analysis, you may like to reduce a force moment combination, that is complete force system on a weak body, a resultant force and resultant moment, resultant force 2G and resultant moment on the body to a single force. You can do that. So this system R and sigma mg, resultant force and resultant moment, is equivalent to a single force R at an offset E, where E is this resultant moment divided by the resultant force. Now, what I have done, this R I have shifted parallel to itself to an appropriate offset so that this fellow's moment about G now equals what here was sigma. So this force system are equivalent. This reduction is sometimes useful in solving problems in an easier way. Now, another point is that this moment business, the moment is about the center of mass and the moment of inertia is also. Now, about any other point also, the angular acceleration will remain the same. Now, for the purpose of analysis, sometimes it is easier to analyze that basically it is expedient to eliminate some of the unknowns to be found out later by taking moments about certain points, which may not be the center. So you may decide to take moments about a point other than okay for your system. But then in that case, you need to take care to include the moment of inertia force. Actually, this D'Alembert's principle is a very nice tool to keep your thinking clear. That is, as all other forces are there, minus mass into acceleration also you consider as if it is an applied force on the body, and then say that when I include that force also, then the whole thing is should be equal. On the right side, it is 0. Similarly, this one also, like inertia moment we apply. Now, if the moments considered mg and not mg, but m about some other point, then in that case, as you take the moments of the other forces, you should take the moment of the inertia force. When you do that, say the point about which you are taking moments is not g but o, then you will get this, and when you take the inertia force, that is this, and its moment about O, inertia force is applicable at G. So its moment about O will be OG plus C. And then this one is equal. So this should be the equation. Then the point about which you are taking moments is something else rather than G. And if you check that AG, what is AG in the planar motion? in terms of alpha, okay, and so on, then you will find that this difference essentially turns out to be mass times the square of the distance between the 2 points. Basically, mass times OG square. So into alpha. So that gives you definitive. That is JO. These two things together will give you minus JO alpha, where JO is the moment of inertia about the point. This is what is really coded in the parallel system. So either you do it like this, or you take the moment of inertia, use the moment of inertia about that. Now this is simple thing that appears in so simple manner for planar. In the case of spatial motion, it's much more complicated. But you might have gone through that because you have gone through the dynamics course. So all this that we are discussing is basically in a way recapitulation. Now we have the actual business. We will do the dynamic force analysis of a forward force. This O2A, B, O4 is a forward force. And I have shown G2 like this rather than I have just tried to point on the link to point out that it is not necessary for the CG of this link to be on the link itself, because as a line segment we show the link only kinematically. The actual link is a little fatter and maybe unsymmetrical. So somewhere nearby 0.2 millimeter. Similarly G2, similarly G4. And these are the centers of mass of the three moving units. By Ri, I am denoting the resultant of all the forces and moments that are acting on the mechanism to link 2, and since they are acting on the mechanism on a whole, this Ri, R2, R3, R4, they don't include the reaction forces at this joint, at this joint, and so on. So these are the forces which are applied more closely on the link directly, including weight, or if something is hanging from that link, or if there is a push on that link somewhere at some point. So all force, moment, everything, when you reduce it to a single force like R2, R2, R4, that is what it is. Fij will be denoting the force applied on link I by link T. So at the point A, whatever force link AB, link 3, will be applying on link O2A, that force will be denoted as F2, and its opposite force which this guy applies on the other will be F3. You know that they are equal and opposite and along the same line. And this notation we will use in all the cases except when j is 1. Because for that you don't need to write fi, because if you write fi without any confusion, we know that that is force applied on I by the same. Okay. So for example, here you will have an F2 on link 2, here there will be an F4 on link 4. And link 1 we don't have to consider because that's not moving. Now, from this, the three moving links, if we disintegrate and make three Y diagrams, then it will look something like this. O2A, on which here, though there is a revolute joint, which does not as by default transmit moment, but there will be an actuator here, so there will be an active moment. M2, and there will be a joint reaction force which is F2 some vector, two unknown components, and this R2 is a known force. Maybe that is the way you can work out, including inertia, but not including the joint reaction. And at point A, you will have F23, force on link 2 by link 3. So in this, you can count the unknowns. M2 is one unknown, F2 has two unknowns, and F23 has two unknowns. Total 5 unknowns. And R2 is 1. Now, when you write the dynamic equations from the force equation, you get two equations, and moment equation gives you one, three equations. So 5 unknowns, 3 equations. You cannot solve it. You take link 3 similarly, and you get 3 equations from here also, 2 force equations and 1 moment equation. And there are 4 scalar unknowns, 2 at this end of the reaction, 2 at this end. So here 4 unknowns, 3 equations. But then one good news is that 2 of the unknowns here and 2 of the unknowns here are very obviously linked by zero. Similarly, when you take this fourth link and consider its dynamics, you get 2 unknowns here, 2 unknowns here, and here no one, because it is a passive, that is not active, without actuator, equivalent, it will not transmit any moment. So there are 4 unknowns and as usual 3 equations. Again, between link 3 and link 4 at this point, F34 and F43 are connected. So out of these 5 plus 4 plus 4, it's actually not 13, but eventually 9 unknowns remain when you consider these two and these two scalar equal. So 9 unknowns and 9 equations. And these unknowns, these equations are linear. And analytical method of dynamic force analysis is just the simultaneous solution of these 9 linear equations. Nothing to really talk about. Except that everybody here may not be very happy, may not greatly enjoy solving 9 simultaneous equations. Of course, I should give you the little good news that these 9 simultaneous equations are equibanded. Quite a few equations will involve only few of them. But they are so coupled and so linked that in order to get the advantage of most of the unknowns not appearing in most of the equations, you will have to do quite a bit of graphical. Analytically, you can do any kind of graphical. There is some problem. But it is some non-trivial computation. And if 4 by itself is non-trivial computation, that's 9 unknowns, 9. Then other bigger mechanisms will be bigger. Okay. Nothing very prohibitive, but there is a very simple way to do it in a step-by-step manner, and that is the graphical. Here I will take a little 1 minute break and rejoin. Okay, so in this step-by-step graphical method, the fundamental idea is that this joint reaction F34, that is force on link F from link force on link 3 from link 4 can be resolved into two perpendicular components, two mutually perpendicular components. One, let us call it F34M3 in the direction of AB. It may be from B to A or the other way around, from B away from it. So whatever it is, that scalar component will be one, and the other is perpendicular. The same force vector noted here by this red arrow, can also be decomposed into two mutually perpendicular components, one along this O4B and the other perpendicular. So if you consider the motion of B related to A, then this direction will be the tangential direction, this direction will be the normal direction. So that is why this is denoted as with superscript N, and the other one is denoted with superscript P. Similarly here, this one is N and the other one is P. Now this red arrow is the vector force which we want to find. Now for that, first consider link 3 and consider this F34N3 and F34T3 resolution. So if we take the total moment, all the moments, including the moment of the inertia force, basically that is already included in R3, okay, about point P. If we take moments about point A, then the force from link 2, that will have 0 moment. So one vector unknown is totally gone from consideration. And since here, for the time being, we are resolving the force F34 into F34N3 and F34T3. N3 running from B towards A or away from A. That is along the line AB. So that also will have no moment about point A. Only F34T3, this little blue arrow, this one will have a moment about point A. And from the moment balance about point A, we will determine F34T3, this component. So this we have determined. Now we consider link 4. And here we take the moments about O4. But now we consider the resolution of this red force vector F34. Now you see F43 actually will be the other way around. Okay. Along the link 4 and perpendicular, component N and component P. And again, since we are taking moments about O4, so the only unknown force which will have a moment will be F34T4, acting at a perpendicular distance O4. So from that we will determine this Vane component F34T4. So for the same force vector F34 in one system of perpendicular directions, we will know this tangential component, and in another set of perpendicular components, we will know this tangential component. Now, and these two do not need to be mutually perpendicular. In general, they are not. But then now we can, from two fragmented information about F34, one from that system and one from this system, we can determine F34 completely. Now we construct F34 completely. How? So if this is the reference point, then F34T3 we know, and the perpendicular component N3 we do not know. We draw a line perpendicular there, whichever way it goes. And in the other system, we know that F34T4, because after we have determined this, it's negative. So F34T4 we draw to scale, and then perpendicular direction wherever it goes. Now these two red lines meet at some point. At which point you get the tip of the force vector, and this vector in magnitude and direction is the F34. Of course, at the appropriate scale. So F34 vector you have constructed completely. Once you have done that, then things will become simple. Then you consider all the forces on link 3. So you get two equations, two force equations, and only two unknowns. The two force components at A, F23, that you determine completely. Then you consider forces on link 4, only forces. Moment you have considered already. So only forces you consider, and when you take the vector balance of forces, including inertia force, then you get F4. Okay. So forces here known, forces here known, forces here known, and finally you come to the link 2. Let me remind you the link 2 till now we have not considered. Now F23 is known. So then on link 2, you straight away write the three equations. Force equations will give you F2, and the moment equation will give you the acceleration moment, F2, which you want. So all the joint reactions. So forces will give you F2, moments. So all the joint reactions you have got, and the acceleration moment also you have got. So this way, at every stage, you are solving just one equation, and from there, all the unknowns in the step-by-step process you can determine. Now it is called graphical method, but you can actually numerically integrate. And at every stage, you will be basically solving one trivial equation. With the same equations that you solve in the graphical method to determine F53 and so on. Okay. So there is not much of a graphical in this, but you can also do it graphically. Analytically or numerically, also you can implement this entire thing in a step by step. Okay. Now the open-ended analytical method for doing like that would be simply simultaneous solution of 9 equations. So this is an easier way to accomplish. Now we come to the final point of our discussion. I wonder whether you could hear the voice in this point. So this procedure I will just summarize once more. Okay. So this you have got because the entire speech that I made on this in this context is written also that the force, the joint reaction force here can be resolved along AB and perpendicular to AB, or alternatively along O4B and perpendicular to O4B. So when we consider moments on link 3 about A, then we consider the first system F34N3 and F34T3 normal potential, and the blue component we determine that. Similarly, when we consider the moments on the 4 about 104, then we consider the other system F34N4, F34T4, and F34T4. Once we have done those two things, then we can construct F34 completely, F34T3, and an unknown particular component, F34T4, along, and then an unknown particular component. Wherever these two red lines showing the unknown perpendicular components meet, that is the tip of the force vector F34. And after F34 is determined, you consider the forces on link 3, determine F23 completely, consider forces on link 4, determine F4 completely, and then finally consider link 2. On that, forces on link 2 you balance and get F2. Now when you say balance, we basically mean input in the inertia force. And when you balance the moments on link 2, you get F2. So this is a step-by-step approach in which at every step you solve just one scalar equation. That's also really not solving the equation, basically the moment dividing the scalar equation, because the force component that we are determining is perpendicular to that distance vector A or O4. Now, the dynamic motion analysis of four-bar linkage. In this, now there is a other problem to forward dynamics. Here, equations of motion for links 2, 3, 4 will give you 9 linear equations in the actuation plot moment M2, and these joint reaction components F2x, F2y, F23x, F23y, F24x, F24y, F4x, F4y, these things, and the three angular accelerations of the links 2, 3, 4. Now, you will also have two more linear equations relating theta double dot, theta 3 double dot, theta 4 double dot from the acceleration analysis. Now, from these 9 plus 2, 11 linear equations, you can eliminate these 8 joint reaction forces, getting 3 linear equations, which, since these are linear equations, that elimination will not be too much of a problem. I mean, by hand, pen on paper, it will be quite a bit, unbelievable, okay, unwelcome. But algorithmically, in a program, it is not a big deal. So, out of 11 equations, when you eliminate 8 unknowns, then you will have 3 linear equations left, from which you can solve theta 2 double dot, theta 3 double dot, theta 4 double dot in terms of the link length, the position coordinates, the velocity coordinates, and the accretion. But now see, in the forward motion, the forward dynamics problem, dynamic motion analysis problem, this M2 is actually known at every time instant of interest. So with known M2T and initial conditions, that is position coordinates and velocity coordinates at some time instant, okay, if that is known, then what it means is basically solving this system of ordinary differential equation. In fact, from here, another little bit of algebra can be done to finally get a single second order differential equation in theta 2 of t. Because theta 3 and theta 3 double dot and theta 4 double dot are actually linear combinations of theta 2 double dot and an acceleration independent term. So that algebraic manipulation you can do, and you can actually get rid of a single second order differential equation on theta 2 of t, because it is a single linear freedom system. So whether you take all of these together or whether you reduce that to a single second order differential equation, you can then use an ODE system solution methodology, which you study in analysis, and get rid of time histories of theta 2, theta 3, theta 4, and their derivatives. There are coordinates and there are in terms of mechanism, the angular positions of mechanisms and angular velocities of the mechanism as functions of time. Basically, tabular values. So this is basically the forward elements. Or sometimes this kind of problems are also known as simulation. Simulation means to mimic mathematically a system in its actual behavior when it is subjected to such and such actuation. So this is dynamic force and motion analysis for a four-body. Now, as you have seen that the process is, at least the analytical process is more or less, procedurally straightforward, though the computation may be quite a big amount. And in particular, the dynamic motion analysis, this thing you can do in a similar manner for other more complicated processes, even more involving more degrees of freedom. If there are more degrees of freedom, then this will not be so easily reducible to a single second order differential equation. There may be two coupled second order differential equations for the two degree of freedom system, three coupled differential equations for a three degree of freedom system. But then the corresponding M2, M7, all those will be given or known as functions of time. So the proposal there is that this and this kind of actuations we are applying. Now find out what kind of motions will execute. What kind of motion will execute. So at this point we stop with four-bond linkage and take up another important mechanism, which is the slider time version of this, in which one of the links is a slider. That is a mechanism which necessitated a much more rigorous and more detailed analysis, and enabled also because that is comparatively simpler and some patterns developed out of that, and it necessarily came from its application in engines. So that we will take up in the